All right. So just like we have done before, so I'm going to spend about 15 minutes also on the material that we didn't finish last time. And then I'm going to give you about half an hour to ask questions before the quiz. Another half an hour for the quiz. So if you have any questions, like I said earlier, you can type your questions in the chat box now. I'll save it for later. Any other concerns other than specific homework questions or quiz review questions? With the limit e to the infinity always. So here's a question. The limit of e to the infinity. So I guess the question is, if you take the limit of x going to infinity of e to the x, is that going to equal to 0? No, that's not going to equal 0, because if you plug in infinity, you get e to the infinity, right? And the e is a number that's more than 1. So any number more than 1, you raise to infinity. It's kind of like multiplied by itself infinitely many times. So infinitely many times multiplied by itself. So the product is going to approach infinity. But you're probably thinking about this. X going to negative infinity e to the x. That's going to be different. That's approximately e to the negative infinity. That's about 1 over e to the infinity. Right? E to the infinity is going to infinity, so you end up with 1 over infinity. That's always going to approaching 0. Good questions. Well, I guess another example you could ask is like, what if I take limit of x going to infinity of 1/2 raised to the x? In this case, the base is not e. If you compare to the first example, the base is half. So that's like saying 1/2 to the infinity. So that's like a 1/2 multiplied by itself infinitely many times. And if you remember that 1/2 times 1/2 is a 1/4, which is smaller than 1/2, multiplied by 1/2 again, it's getting smaller, right? So every time you multiply by 1/2, it's actually getting smaller. So this one is approaching infinity. Kind of like a e to the negative infinity case. Good question. All right. So like I said, if you have more questions, don't feel free to ask them later or now. I'm not familiar with you, Aiden. I don't know what you mean. What about negative? You mean a negative number raised to infinity? Oh, you talk about, okay. Are you talking about limit x going to negative infinity? Okay, I'm not sure what you meant, but let me write down 2 examples and then you can ask. Are you talking about this case? Or are you talking about limit? Okay, good. So this case, again, let's just look at it, right? So just one step at a time. So this is, if we plug in negative infinity, we get 1/2 to the negative infinity. There's a couple ways you could go. One, you could just rewrite it in terms of 1 over something. So that's to get rid of the negative in the exponent. So that's like a 1 over 1/2 to the infinity, right? If I drop the negative exponent, and that becomes 1 over, from the previous example, 1/2 to the infinity is 0. So that's about 1 over 0, right? And that, so if 1 divided by something really, really small, it actually gives you some number that's really big. So that's actually approaching infinity. Another way you can look at the problem is that, can I take 1/2 and then rewrite it using negative exponent? So that would be 1/2 is 2 to the negative 1, right? And outside you get negative infinity. So 2 raised to 1 exponent, then raised to another exponent is equivalent to multiply by the exponents together. So that's 2 to the -1 times negative infinity is 2 to the positive infinity. And then what is 2 to the positive infinity? Well, that's like a kind of e to the infinity case, right? So that go into infinity. So it doesn't matter which way you look at the problem, you're going to end up with infinity as a limit. All right. Good question. Yeah. So if you're not sure, just think about it's infinity is something multiplied by itself, right? Good questions. All right. So let me finish what I didn't finish, and then I'll give you enough time to ask questions. So I am going to begin with the theorem, just get it out of the way. So this last time we talked about 3 theorems. So I guess let me make a note. So what I'm going to cover today, like from now on, before the quiz review. So today material is not going to be on the quiz. But what we talked about before today, that could be on the quiz, right? It's not on quiz. Just so that way you don't have a panic. So we talked about 3 theorems last time. So this is the fourth one. It says if the limit n goes to infinity of an, remember an are terms of a sequence, is equal to L. So that means that the sequence approach a limit L. And this means n function f is continuous at L, then we can see that limit n goes to infinity f of an. So if an is the input of f, the continuous function, as for n goes to infinity, that if that's the case, we can simply bring f, the function, outside and just take the limit of the input first. And I'll give you one example to show how that works. And that is equal to f of L, because this part, limit of an as n goes to infinity, that's has a limit L. If we use the substitution there, so we get f of L. So that's what this theorem says. An example would be, for example, if we want to find the limit n goes to infinity of sine pi over n. Is this the last theorem? No, this will not be the last theorem. In fact, this chapter has a lot of theorems. Just like I said yesterday, this material is related to real analysis of, functional analysis. There's a lot of theorems, definitions, but I'm not going to make you to prove any theorems, but you just try to understand them and then use them. So here we try to take the limit of this term, sine pi over n. And you probably think, can we just find it? Well, one way you could do is that you could calculate one of them at a time. For example, you can write down that. You can think about this is the elements of the sequence, right? Write down each element. You can write down plug in 1 sine pi over 1. You can calculate that number, and then calculate sine pi over 2. Calculate the value, and the sine pi over 3, and then sine pi over 4. You can calculate each one of them, see what they approach to, right? To try to find the value that this sequence approached to. That's one way. But another way is that, sort of using the theorem here, is that you can look at this as elements of a sequence. And then you can think about sine is just a function, just like the function I'm writing in the theorem above. So this is like taking the limit of f of an, if you look at it that way. So the f is a sine function. right? So we know just by kind of like thinking on the side, we know that we can take the limit of pi over n as n goes to infinity. That's okay to do, right? I mean, we sing example like a 1 over n, and we take the limit. That's okay. If you have pi over n, we can still take the limit of this sequence. It's going to has a limit, some number, right? We can talk about that later. But we just know that sequence will have a limit. We know that. And we know sine is a continuous function, right? Sine f equals sine of x, that's a continuous function. So we have, in this example, what we have is that we have the limit of the sequence exists, and we know the function is continuous at that limit. The sine function is continuous. So we have both. That means we can try to apply the theorem directly, which says we can bring the function outside. So the function is sine, so I'm going to bring it outside. So that becomes a sine of, put the limit inside, n goes to infinity of pi over n. So we can figure out this limit first, and then we can take the sine of that part, that limit. It might be a lot easier than focus on the whole sequence sine something. So let's consider this. So what is the limit as n goes to infinity of pi over n? Well, if n goes to infinity, pi over n becomes, so let me leave the sign alone. So pi over n becomes pi over infinity, right? What does the pi over infinity, if you take pi, you divide it into infinite many parts? It's very small, right? So this part basically approaches 0. And then you basically take sine of 0 there. What is sine of 0? 0. So you don't even have, so the benefit of this theorem is that you don't even have to, do a lot of calculation for each one of them, to see the pattern. You can find the limit easily that way. Just want to point out. So this is the one theorem that's a benefit of it. That's the last theorem for today. Any questions on this theorem and the example I gave? And I believe, I want to remind you, because I just think about it. In the past, we actually have something like this. If you remember that we had a long time ago, I think it was I'm going to erase it in a second. I think it was a problem like find the limit of x to x or something like that as x going to infinity. I remember what we did is we take x to the power of x, we write it as e to the natural log of x to the x, and then we bring x in front of there. And then we keep the limit and then write as e raised to the x natural log of x. That's what we did, right? And then if you remember that back then, what we did, because e to the something exponential function is a continuous function, so we bring the limit to the exponent part and end up finding the limit of the exponent first using L'Hopital's rule. I don't know if we did it in this class or maybe in a calculus 1 class. I definitely feel like this is new. This is like a fresh to me. So we find the limit of the exponent first and then find the e to that limit. So that's the same thing because e is a continuous function, just like here. It's basically the same idea. All right. I just want to point that out. Any comments or questions? All right, I'm not hearing any questions, so I'm going to continue. So there's a few definitions. the next thing I'm going to talk about is called monotonic sequence. So you can think about mono, right? Means singular behavior, right? So just one type of something, one type of behavior, right? Monotonic. Mono means one. So definition: a sequence an. So I'm not going to use n equals 1 to infinity, but it's there, right? Just assuming that sequence. A sequence an is increasing. So we call it a increasing sequence if an is always less than an plus 1 for all n. So for all, remember this means for all, upside down a, for all n greater or equal to 1. That is, if you expand it, that means for all n greater or equal to 1. Another way to see it is that a1 is always less than a2, less than a3, less than a4, and so on. So that's the later element is always bigger than the previous one. So that's an increasing sequence. And obviously you can write down the one for decreasing sequence. So a sequence an is decreasing or decreases if an greater than an plus 1. So the an is bigger than the element that's coming after it for all n greater or equal to 1. So that's sequence being increasing and a decreasing. And another one, so a sequence is monotonic if it is increasing or decreasing. So if you have a sequence that's increasing, that's monotonic. If you have a sequence that's decreasing, that's also monotonic. Monotonic just means increasing or decreasing sequence. Sometimes we say it's monotonic increasing. Sometimes we say it's monotonic decreasing, but it's the same. So those are the definitions. I think it's fairly straightforward if you just think about the elements, right? And the sequence. So here's the exercise. Is the sequence, I'm not going to write down here. It's the sequence -3 over n plus 5. Is this sequence monotonic? If it is it increasing or decreasing? Well, how do we find out? We can start making a list, right? We can make a list and then look at the elements, see if it's increasing or decreasing. Or we could just directly, so this is what I like to do, is sort of taking a little bit longer route to some of you, but I like it because it's using the definition of increasing and decreasing, because we're comparing an and an plus 1, right? The element coming after. So yeah, it is decreasing. Okay. Is it decreasing? I have a feeling that it's actually increasing. But let's find out, right? So what I'm going to do is I'm going to write down an, and I'm going to write down an plus 1 and find the difference. So an is equal to, just by definition, is -3 over n plus 5. And the an plus 1, if we just increase the n by 1, everything should stay the same, right? So that should be -3 over instead of n, it's n plus 1 plus 5. I can write it as negative 3 over n plus 6. That's the term coming after an, right? And then the next thing, if I want to compare which one is bigger, what I do from what I learned from my teachers is that I always find the difference. So I'm going to calculate an minus an plus 1. I want to know if the difference is positive or negative. If it's positive, that means the first number, the an is bigger. If it's negative, the one I'm subtracting is bigger, right? So I'm going to calculate negative 3 over n plus 5 minus negative 3 over n plus 6. And here I'm just going to common denominator. So I get negative 3 times n plus 6 minus negative 3. So that's a plus 3 times n plus 5 divided by n plus 5 n times n plus 6. And expand the numerator. It's only in the numerator part. The denominator, in this case, both are positive, so we don't have to worry about it. So I get negative 3n minus 18 plus 3n plus 15. So that's n plus 5, n plus 6. And I'm going to cancel 3n in the numerator. I get negative 18 plus 15, so I end up with negative 3 over n plus 5 times n plus 6. And to keep in mind that my n value is always going from 1 to infinity, right? So n greater or equal to 1. So if n is positive, greater than or equal to 1, this term is positive. This term is also positive. The negative 3 is negative. So overall, I end up with a negative number. Right, so let me write it again. So the numerator is negative, the denominator is positive times the positive. Denominator is positive, but numerator is negative. Right, so we're not using any identity here. It's sort of like, yeah, I'm just using algebra. This is just a whole bunch of definitions and they use it on your own, on its own sort of. So I get negative number. So if an minus an plus 1 is negative, right? So I'm finding the difference between those two. The first number minus the second number end up to be a negative number. So that means the one I'm subtracting is bigger, right? Like a 3 minus 5 is negative because 5 is bigger than 3. That's why we have a negative, right? So therefore, so because we end up with a negative number, therefore an is less than an plus 1. So the number that's coming after an is actually bigger. So this is a bigger number, this is a small. Therefore, because the number that's coming after is bigger, so it's increasing. But good guess. That's what we do, right? We sometimes guess, we sometimes look at for pattern, try to make a conclusion. So we just solve for an. No, we're not solving for an. We want to know which one is bigger, right? We want to know if the sequence is increasing or is the sequence decreasing. We want to know the value of the sequence is getting bigger or not. That's what we try to figure out. We didn't solve for anything. We find the difference between an and the number next to it, like after that, and we figure out that's the difference is negative. That means an is subtracting a number that's bigger than itself. So that's why we end up with a negative difference. So we end up finding that the value in the sequence is increasing. Therefore, it's monotonic. could we just plug in n equals 1 and n equals 2 to see which one is larger or smaller? Yeah, why not, right? But this is I cannot think about an example, but mathematically, you have to be very careful because you might have a formula, let's say you plug in the n equals 1, n equals 2, and not finding, one of them is bigger. But is that really is the same pattern going to follow for other n like one n gets bigger? I mean, there's all sort of weird examples for math out there, right? So just be careful. I would say be careful for this specific question here. Yes, it is. It is monotonic, but you might have a sequence that let me think. Because I'm thinking about something that again, I'm not going to have time to work on it, but let's see. What about this sequence? N minus 2 squared. If you have something like this, you put 1 there, so you get 1. If you put 2 there, you get 0. Right? And yeah, if you put 1 there, you get 1. If you put 2 there, you get 0. You might conclude that, oh, that sequence is decreasing. Right? But then if you put 3 in there, you get 1 again. And then you put 4 there, you get 4, right? 4 minus 2 squares 4. And then you put another one, you get a 9. Right? So what about this? Is this sequence increasing or decreasing? The answer is that it's not monotonic. It's not increasing all the time. It's not decreasing all the time. So we don't see this for this sequence I gave you. It's not increasing. It's also not decreasing. Just it kind of increasing and decreasing, in different parts. So this example, I just want to show you that just take n equals 1 and n equals 2. In some examples, you're not going to have a you're not going to reach the correct conclusion. The reason the previous example works is because if we treat it as a function, it's I think it looks like this, something like that. I might be wrong, but this example I'm giving you, it goes down and then going up. So you have a sequence that decreases and then increases. So that's how weird that example is. Sometimes you might have a sequence that going up and then going down again, right? So is it increasing or is it decreasing? Right. So yeah. So Aiden. So if the sequence, going from positive, like increasing, decreasing, then increasing, it's not monotonic. It has to be like just one behavior. It cannot have increasing and decreasing at the same time. Okay. So you could follow what I did with the n and n plus 1. You're going to notice that you're going to have a problem. So you're going to reach some expression with n, but that's not always positive or always negative for all n greater or equal to 1. I'm not going to have time to do that, but I just want to show you this. All right. Right, yeah, alternating series. That's also a good example. If you have something that going from positive to negative and then positive and negative, excellent example, Chris. I'm going to put it here. Thank you. Sequence. Good. All right. So I'm going to have another definition. Bounded sequence means the value of the elements in the sequence is bounded. It doesn't blow up. So a sequence is bounded above if there is a number m, capital M, such that st, such that, right? Such that an less than or equal to m for all n greater or equal to 1. M is called the upper bound of the sequence. I'm just going to use this notation for sequence. I probably should write a sequence an is bounded above if there's a number, capital M, such that all the elements in that sequence an is less than or equal to m for all n greater or equal to 1. So that's a bounded above. Sort of like, having a cap on how big the elements could be in the sequence. And then another definition, a sequence an is bounded below if there is a number lowercase m such that an greater or equal to lowercase m for all n greater or equal to 1. And the lowercase m is called the lower bound. Oh, no, lower bound, sorry, lower bound. So that's just upper bound and the lower bound. A sequence an is bounded if it has an upper bound and a lower bound. So it must have a sort of a threshold above and one below. That case is called bounded. If one of it is missing, it's not called bounded. So that's the definition of being bounded. This one is called being bounded up below. That's being bounded above. Has to correct. So in order for a sequence to be called bounded, it has to have both lower and upper bound. That's the definition of being bounded. If it just have a lower bound, you can see it's bounded below. It doesn't mean that it's not the same as being bounded. It's just being bounded in one direction. Be careful with the terminology. And here's, I said this, I think I said theorem 4 was the last one, but here's one more. So theorem 5 is called the monotonic sequence theorem. This is the last one. So this one is really simple. So every bounded monotonic sequence is convergent or converges. Or you can say it's convergent, doesn't matter. So that's the theorem. If you want to show something is convergent, you can try to see if it's bounded. and then to see if it's monotonic, it has to satisfy two conditions. Monotonic means it's always increasing or always decreasing, right? Bounded means the value of the terms doesn't go above and below a certain number. I'll give you an example. If one of them is missing, then it's not convergent. For example, you might have a sequence that's monotonic decreasing, but it's bounded above, it's just not bounded below, so it's not bounded. Even though it's monotonic, but it's not bounded, so it's not convergent. So here, this example is bounded above. So I'll just say not bounded. Right? Therefore, it does not converge. An example, like Chris said earlier, you might have a sequence that's bounded, like an alternating sequence, like this one, above, below. The value of this sequence doesn't go past this highest value, and it doesn't go below this lowest value. So it has up and a lower bound. So it's bounded, but because of the elements, the alternating signs, right, going from one element to another, then going up and sort of like a decreasing, increasing, decreasing, increasing. If you look at the values, so it's not monotonic. So this sequence is not convergent. It does not converge. So you have to have both, so not convergent. So you have to have both parts satisfied for it to be convergent. Obviously, you might have a convergent sequence that's not monotonic. That's okay. So what I'm saying is, like, if you kind of going backwards, like what we call the converse of this. So every bounded monotonic sequence is convergent, but doesn't mean that every convergent sequence is bounded and monotonic, right? That's a converse. That converse is not true. So let me give you a couple examples on the. What will you look for when proving something isn't monotonic, like with a negative positive sign? And would the result not be positive or negative, or would it be zero? If it depends. If you have an alternating sequence with a plus and minus sign, the elements alternating, it depends on the limit, right? So you could have alternating at the beginning, positive, negative, but then eventually the positive will approaching a negative value. So the negative is actually the limit. So it really depends on you have to be very careful. So it doesn't mean if a sequence has a few numbers that's positive, negative, alternating, but doesn't mean it's always going to be like that. You might have a sequence, I'm trying to draw, you might have a sequence that's sort of going like this. It's positive, negative, alternating, and then eventually all of them will fall below the negative, fall in the negative region. So the limit is actually approaching a negative, it's not a zero, right? I just want to show you that you have a case like this, it's convergent, but it's not monotonic. It's bounded, right? So that's that's a good example. So the converse of this theorem. All right, let me give you a few examples. Maybe that will help make more sense. For example, so for the following example, determine if given sequence is monotonic, bounded, or convergent. I'm going to take the previous example that we already had, -3/n+5, this one, right? This one we know, earlier we said it's monotonic, increasing. That's what we showed earlier through the an minus an plus 1, right? We showed that's the sequence, it's monotonic and it's increasing. Means that the value will always getting bigger each time, right? Now, is this bounded? Is this bounded? Wait, did it run? No, let me double check. I hope I didn't screw up on this. -3. Okay, that's right. That is right. I didn't do anything wrong. So for this one, the value is increasing. But is this bounded? Is that like a lowest value and the up and the highest value that all elements will fit between? Well, if it's always increasing, so that the elements always increasing, so that means the first element will be the lowest value. So the lowest value is going to be -3/1 + 5. That's the lowest. What about highest value? So does those values sort of approaching some limit eventually? Well, let's take the limit as n goes to infinity. Right? So limit n goes to infinity will give me the highest value it could reach. If n goes to infinity, what does this goes to? This goes to -3/infinity plus 5, which is about -3/infinity. That's going to go towards 0. So the value is increasing each time, but eventually it's going to reach a limit 0. 0 will be the highest value that the sequence is going to approach to. So if the sequence, we find out that it has a lowest value, -3/6, which is -1/2, and a highest value, the limit, is approaching 0. So that means this sequence is bounded, right? It has a lower bound and an upper bound. So this sequence is bounded. It's monotonic and it's bounded. Therefore, it's convergent. All right, so Frank has asked question, why did I plug in 1 for the lowest? So recall that earlier, we found out that it's monotonic increasing, right? The previous example I did. So earlier we said when we look at this example, we did a whole bunch of work. We found out that the sequence is increasing for all n greater or equal to 1. So it's monotonic increasing, right? It's always increasing. If a sequence is always increasing, the value is getting bigger each time as n increases. So therefore, the lowest value coming from the first element when n equals 1. That's what I did. Because it's monotonic increasing, so the first element is always the lowest value because it increases each time. Yeah. So that's why I plug in n equals 1, because n equals 1 is the lowest value we could plug in for n. And that because it's increasing, so we know that when n goes to infinity, that will give us the biggest value in the sequence, right? Because it's increasing. So what I did, the next is I took the limit as n goes to infinity, to figure out what the biggest value is approaching to. And the biggest value I found out is by taking the limit, that's going to go to 0. So the 0 is sort of the up limit that's approaching to. And the sequence is bounded below by -1/2 and up above by 0, therefore it's bounded. Now, I didn't draw the dots correctly. Maybe that was confusing. The dots should be something like -1/2, and then it goes up. It's still increasing, but it's sort of like a curving towards the x-axis. So that's increasing and bounded above, and below is already bounded by -1/2. So we always plug in 1 to find the lowest bound. It depends. So this example is always increasing. So the lowest value is when n equals 1, right? The first element of the sequence. That's what gives you the lowest. But if you have a sequence that's decreasing all the time, you wouldn't plug in 1 to find the lowest bound, because if you put 1 there, if it's decreasing, then the first element will be the highest value, right? So that will give you the upper bound. Take 1, put in there. Same thing with taking the limit. Depends on whether n goes to infinity will be the lowest value or the highest value. You have to look at the sequence being increasing or decreasing. Kind of just think about a function. If you have a function increases, a small x value will give you a lower value. A large x will give you a highest value. Right? Same idea. Just sequence. Here we just talk about different points instead of a continuous function. All right, let me give you another example to hopefully that will make a little bit more sense. So here's the second example. Again, we're going to figure out whether it's monotonic, bounded, or convergent. (n/n+1), the sequence. Well, the first thing I'm going to do is I'm going to figure out whether it's monotonic or not. Right, whether it's increasing or decreasing. So I'm going to write down an on the side is (n/n+1). an+1, just n+1, not the an+1 is in the n is added 1. So that's (-n+1) divided by, oops, oh no, it died. Almost done here. Sorry, my pen died. Let me charge it. I'm almost done with this example here. So (n+1 over n+1+1). That's an+1. I'm going to rewrite as (-n-1) divided by n+2. So I want to know if it's increasing or decreasing. So I'm going to find an minus an+1. Find the difference. So that's a (-n/n+1) minus (-n-1 over n+2). Again, I'm going to common denominator, n+1, n+2. And in the numerator, I have (-n) minus (-n), that's a positive n. And then -1, that's a +1. So I got 1 over n+1, n+2. And then remember that n is greater or equal to 1. So n is always positive and it's always more than or equal to 1. So I get positive number in the numerator, positive in the denominator. So overall, it's a positive number at the end. If the difference is positive, so that means this one I'm subtracting the an+1 from, this one is bigger, this one is smaller. So a big number minus a small number, you get a positive, right? So so that's the case. So the first number is bigger than the number coming after. So this is a decreasing sequence for all, because we figure out it's positive for all n greater or equal to 1. Doesn't matter what n is. Did I forget to distribute the top for common denominator, or am I wrong? I did, right? Because so here I had a so negative n minus negative n plus. Oh, bummer. Thank you for pointing out. I don't know. Let me erase this. Sorry about that. I did this whole thing all wrong. How stupid I was. Anyway, so let me redo this. I did forget to actually do the common denominator. I hope I didn't make the same mistake in the previous example. So I'm going to negative n times n plus 2 minus negative n minus 1 times n plus 1 divided by the common denominator n plus 1, n plus 2. So that will be negative n squared minus 2n, and then be careful here. So that's I'm going to bring a negative. I'm going to just leave it there. So negative n squared minus n minus n. So that's a negative 2n, and then minus 1. Denominator stays. So that becomes negative n squared minus 2n plus n squared plus 2n plus 1. Oh, okay, great. N plus 1. Thank you. I did forgot to do this, but it turns out that we still have 1 in the numerator, and the denominator is the same. Funny, nothing changes there. Okay, thank you. So we still conclude that it's a positive number at the end. So we end up with decreasing sequence for any n greater or equal to 1. So it's all, so this is a monotonic decreasing, right? If it's monotonic decreasing, that means the value is getting smaller each time. So the biggest value is given by the first element, the smallest value is given by the last element as the n goes to infinity. So this sequence decreases. So the first element, n equals 1, will give me the biggest value. So that's a negative n, which is negative 1 over 1 plus 1. So that's a negative 1/2 again. Weird. And then the last element is given by as n goes to infinity. So I'm going to take the limit as n goes to infinity of negative n over n plus 1. If you remember, we had something like this last time. So we're going to divide by n directly. So that becomes limit n goes to infinity of negative n over n divided by n over n plus 1 over n. And if we take the limit, simplify and take the limit, so that becomes negative 1 over 1 plus 1 over n. As n goes to infinity, the 1 over n goes to 0. And then we just end up with negative 1. So the smallest number is negative 1. The biggest number is negative 1/2. Right? So this sequence is bounded because you can figure out the lower bound being a number, the upper bound being another number. So this is bounded. And it's monotonic, it's bounded, therefore it's convergent. How do you find the bounds? So you always want to find out whether it's increasing or monotonic, increasing or decreasing first. That will make it easy to find the bounds. Because like I said, because we found out that this is a decreasing sequence, so that means the value decreases each time, right? So where does the biggest value happen? The beginning element. Where does the lowest value happen? The last element. Well, the last element is just 1 and goes to infinity. So that's what I did. To find the biggest element, I know it's the first one. So I take n equals 1, put in there into the formula, and that was negative 1/2, right? And as n goes to infinity, the value decreases until it gets to the smallest. So that's why I take the limit as n goes to infinity to give me the lowest value. Now, be careful though. Lowest value doesn't mean it's going to go to negative infinity, right? even though you have a sequence that decreases each time, it doesn't mean it's going to keep decreasing until it reaches negative infinity, because you might have a sequence that going like this and then sort of flat out, but it still decreases each time. It just decreases a lot slowly, right? So decreasing could decrease towards a lower bound. That's what I meant. All right, so that's that example. Can I take 1 minute to go through another example really quickly? I think that probably helps understand this, like, you know, the divergent case. I'll be really quick, then I'll give you time to ask questions. So here's a sequence, negative n squared. Is this monotonic increasing or decreasing? Well, an is negative n squared. An plus 1 is negative n plus 1 squared. Right? So let's just find an minus, you can probably tell by just plugging numbers, but just in case, minus an plus 1. So that's a negative n squared minus negative n plus 1 squared. That become positive. So that's a negative n squared plus n plus 1 squared. I'm going to expand that. That's a n squared plus 2n plus 1. We end up with 2n plus 1. And this I know for n greater than equal to 1, this is always positive. So this sequence is monotonic decreasing. So it's monotonic, it decreases all the time. But is this bounded? Well, if it decreases, the first value is given by n equals 1, just like the previous example. So if we put 1 there, so we get negative 1 squared, negative 1. So this is the upper bound, the biggest value. What about the lowest value? Because it decreases, so the lowest value is given by when n goes to infinity. What is the limit of this when n goes to infinity? Well, if you kind of just looking at it, right? Negative infinity squared, you get negative infinity. This is not a finite number, so it's not bounded. Not so the sequence, it decreases, is bounded above by negative 1, but it's not bounded below by a finite number. So it's not bounded. It's monotonic, it's not bounded, therefore it's not convergent. We cannot say it's convergent. In fact, it's not convergent in this case. Because you could just think about, you know, the value going from negative 1 and decrease all the way to negative infinity. The limit is approaching negative infinity, so it's not a convergent sequence. All right, I'm going to stop there. Sorry for taking a little bit longer than I planned. I will give you enough time to ask questions about the quiz or about this material. Okay. All right, go ahead, Aiden. And the same, you can also ask your questions to maybe the.
So it's the end of a problem, but it's finding the integral of one part. It's the integral of negative 1 over x squared plus 6.
Negative 1 over x squared plus 6?
Yeah.
Like this?
Yep.
Okay. I think for this one, you cannot use partial fractions. You kind of just have to use for me, when I see this, even though it doesn't look like an a squared, x squared plus a squared, the denominator, x squared plus 6, we can treat it as x squared plus square root of 6 squared, with the a being square root of 6, and then we can use trig substitution, x and the square root of 6 here. Does that kind of help, Aiden?
Yeah.
Is it okay if I don't finish it? Because from here you the negative one always bring it outside. Forget about it. I mean, not forget about it. Leave it aside. And then so dx equals square root of 6 secant squared theta d theta, and then you can figure out x squared plus 6, which has become square root of 6 squared. That's a 6 tangent squared. Theta plus 6, so that's a 6 tangent squared theta plus 1, which is 6 secant squared theta. If you put back in there to integrate -1, negative outside, you just get 1 over 6 secant squared theta, and then you have 6, no, not 6, dx is square root of 6 secant squared theta d theta. So bring the square root of 6 and the 6 outside, so negative square root of 6 over 6, integrating, and then just 1 d theta. I say you can finish it from there. Let me know if you have more questions on this. Sam, I know you came to office hours. Do you have any questions?
Not about that. I got it figured out, but could you maybe explain the like after you find the monotonic again, could you explain what happens after that?
Well, what I'm trying to do is that I'm trying to, so for all those the last few examples I gave, right? So what I'm trying to do is I'm trying to decide if it's monotonic, means that is it always increasing or always decreasing? That's what I'm trying to find out, right? And then I'm trying to find out whether it's bounded or not. And then the last part I'm trying to find out is whether it's convergent. The theorem says if it's bounded and monotonic, then it's convergent, right? So if I get yes to the first two parts, then I can say it's convergent. That's what I tried to do. So for all those examples, what I did is I first decide if the sequence is always increasing or always decreasing by finding the difference between an and an plus 1. Use that to decide if the sequence is increasing or decreasing. And then after that, I need to know if it's bounded from above and bounded below, because that's what bounded means, right? It means bounded from above and below. So what I did is for each of the example, after I know it's increasing or decreasing, I figure out the lower bound by using the either the beginning or the ending value, the beginning value or of the element. I mean the value of the beginning element, or the value of the last element. So to do that for the beginning element, it's either you just take 1 for n, plug in. For the ending element, you have to take the limit as n goes to infinity. That's what I did to decide if it's bounded. It only works for monotonic. If it's not monotonic, you cannot find the bounds this way. You have to, there will be other tricks that we can use, other techniques that we have to adapt. Because think about monotonic means like just always, right? Always increasing, that's monotonic increasing. Always decreasing, that's monotonic decreasing. If it's always increasing, then the first element is the smallest, the last element is the biggest. So that's the idea. For monotonic sequence, it's a lot easier to find out the lower and the upper bound, because it's either going to be the beginning or the end. for yeah, so that's what I did. I figured out whether it's bounded, and by finding the lower bound and the upper bound, and then from the monotonic and the boundedness, I conclude whether it's convergent or not.
I'm sorry, but can you just explain on the last one, like that we did how to get like theta, like translating from theta into x?
Oh, like it's the next couple steps?
Yeah.
Okay, yeah. Sorry for jumping back and forth between different examples. So going back to this example that was asked earlier. So after we get to this point, you get -√6/6, and then integral of 1d theta is just theta, right? Obviously, you have a plus a c or something. But then the given integral is in terms of x, so we cannot just leave it like theta. We have to write theta in terms of x. How do we find theta in terms of x? So now we go back to the beginning, what we did with substitution. Beginning, we said x equals square root of 6 times tangent theta. So that's a relationship that relates x to theta. We can use that. So let's kind of rewrite that equation. Or you can look back at the right triangle. So from here, we know that we want to solve for theta. So x over square root of 6 is tangent theta. And then I can take inverse tangent or arctan on both sides. So you get inverse tan of x over square root of 6. That's equal to theta. I'm going to take this, substitute for the theta in that answer there. So that becomes negative square root of 6/6 inverse tan of x over square root of 6 plus a c. So that will be the answer in terms of x. Okay. So yeah, so when you want to go back to the original variable, you always want to go back to the substitution that you made earlier, right? Like wherever the substitution begins, like here, this is sort of the beginning of that substitution. You go back to that relationship, you try to rewrite it in terms of the variable that you begin with. If you use multiple substitutions in that process, then you kind of go back one step at a time until you get back to the original variable. Quiz time? Okay, it's almost time. Any other questions? I got yelled at by a few students last time because I started a bit early and then messed up with the ending time. I'm gonna be careful this time, make sure that I would like to see more example for review, but I don't have any on hand. Well, let's see. I can think for anything. I cannot think about anything, but let's see. I'm just making things up, right? Right. Don't worry about dropping the lowest quiz. You probably wouldn't, I don't think any of you need to, drop a lowest grade now because most of you did really well. even if you didn't do well on one quiz, I think overall you did pretty good. So don't worry about that. Like I said, from the beginning, just do your best, that's all. So problem on the quiz, you might have a problem like, going from 2 to infinity of some function f of x dx. All right, go ahead, Frank.
So this one was from the homework. So it's the antiderivative of 37 over x minus 1 times, in parentheses, x squared plus 36.
Okay, this one.
Yeah, that one.
So we're integrating this, I suppose.
Yeah.
Sorry, what's the question?
So this one, this is the example that we have to use partial fractions, because it's more difficult to integrate directly. So, but we can take this and separate it. So let's just leave the integral. Let's focus on this. Let me use a different color. Let's just focus on this part. We're going to take this fraction 37 over x minus 1 times x squared plus 36. We're going to break it into fractions, that simpler fractions, right? So the first, if you recall that the factors in the denominator here, the first one had just, it's a linear factor, x minus 1 with a power 1. So that would be just x minus 1 as a denominator. The second one also has it's a quadratic x squared plus 36, but has a power 1 as well. So that will be the denominator of the second fraction, x squared plus 36. But then you have to find out the constants related to them. So the first one I'm going to add a. The second one, because the denominator is quadratic, so I'm going to write as ax plus b, right? Oh, sorry, not ax plus b. I already used a, so that will be bx plus c. Doesn't matter, just two new variables. And how do we find the a, b, and the c? Well, to find the a is a little bit easy. What we're going to do is that we're going to multiply by x minus 1 to all terms, so that x minus 1 will cancel in the a term, and also in the fraction on the left. And then we're going to plug in x equals 1 to make the b and the bx plus c term go away if I put 1 there. The a, it's already by itself, so that's not affected. The left side is okay. So if I do that, so I get 37 divided by 1 squared plus 36. That's good. That's equal to just a. All right, the bx plus c, that's become a 0. So that's a equals 1 after I simplify the fraction. How do I find b and c? We cannot really plug in any x value to cancel out, right? So Aiden has a question, if those two factors are flipped, like if you have 37 over x squared plus 36 over times x minus 1, absolutely, you can call any, you just have two fractions, right? You still have the same fraction. You can call this c or you can call this a, doesn't matter. It just represents a constant that I'm looking for. Right, so it doesn't matter. You can call that a, you can call this bx plus c. Doesn't matter, right? So to continue this, to find bx, b, and c, so what we're going to do, we're going to take the original one, the one I wrote in orange color. I'm going to multiply by the denominator on the left to every term. So if I do that, I'm going to use orange to continue. So if I multiply by the denominator in orange to all terms, before I cancel out the x minus 1. So I get 37 equals A. A is 1 times 1. Oh, let me write it down. A is 1 over x minus 1 times x minus 1, x squared plus 36, plus bx plus c, divided by x squared plus 36 times x minus 1, x squared plus 36. Right? And then I can cancel out a few terms and simplify the term on the right. So that will give me 1 times x squared plus 36 plus bx plus c times x minus 1. So that's bx squared minus bx plus cx minus c, if I expand it correctly. So now I'm going to collect like terms and try to match the coefficients with the terms on the left. So I got 1 plus b, those are the coefficients of x squared. And then I'm going to put together the coefficients of x, that's a negative b plus c of times x. And then the constants I have is positive 36 minus c. So those are the constants I have. And that should match with the terms on the left. The terms on the left, I only have 37. I don't have x squared. So you can, assuming there's a 0 times x squared and a 0 times x and a plus 37, which means the 0 of the x squared has to match with 0 of 1 plus b. So 0 1 plus b. So we can find b there. And the 0 of the x term must equal to negative b plus c. And the constant 37 must equal to the constant on the right, 36 minus c. So b and the c that we find must satisfy all 3 equations. If one of them is not satisfied, we got an issue, right? So here we can solve for b, which is negative 1. We can solve for c. If we put negative 1 in here, we get positive 1. So c is also negative 1. And then 36 minus negative 1 equals 37. So yeah, so that works. So it works too. So that means b and c are correct. We didn't reach any contradiction. So now we have a, b, c. Let's rewrite the equation. So the integral, we're looking for 37 over those 2 terms in the denominator. So that becomes integrating. A is 1 over x minus 1 dx. I'm going to continue plus. B is negative x, c is negative, b is negative 1, c is negative 1. So that gives me negative x minus 1, x squared plus 36 dx. And then we can integrate each one separately. And when we integrate the second term, you might want to separate the fraction, separate it as negative x over x squared plus 36 dx. And then separate the negative 1 over x squared plus 36 dx. So you take one fraction, you separate it using partial fractions, divide it into 2, but then it's easier if you continue to separate into 3 here. You may not have to do this. Maybe you end up with something that's a lot easier to just integrate directly. But in this example, it's easier if you separate each one of them separately. This one, you're going to be okay. This one, I think it's okay if you use u-substitution. I don't think it's really that difficult because you get an x in the numerator, right? And this term, the last integral, I don't think is too bad, given that we just talked about one example earlier, but because the denominator looks like x squared plus 6 squared, you can use u-substitution. Okay, any questions on this? I don't have time to finish it, but hopefully that's enough work to get you started on problem like this. So let me just note that if you see something like this, you may not need to separate into two fractions. Depends on what you have. Sometimes it's easier you separate. Sometimes it's easier just take what you have and integrate directly. So look at this example and do your best, I guess. Any other questions? Last chance. Shall we take the quiz?